Next we have Erich Mueller from Cornell to tell us what ultra-cold atoms teach us about strange and bad metals.
So thank you very much. I'd like to thank the organizers and all the previous speakers. I've learned a lot from this, this workshop so far. So I'm going to start with just an advertisement. We're doing a job search this year. If you know of some young experimentalists, please send them our way. So I think the crucial question, why are we here? And really, in my mind, we wanted to know how generic the phenomena are of strange metals and bad metals, right? That is this a very particular thing that has maybe a different source in different materials? Is a strange metal in a high TC the same as a strange metal in a heavy fermion material? Is it a generic feature? Whenever you have strong interactions, you're going to get this sort of properties happening. And the hope is that by using these very controlled experiments that you can do in cold atoms, that we can systematically address the different possible ingredients which could be the source of these behaviors. Okay? So where should we start? And I think the natural place to start is just the Hubbard model, right? It's the simplest model of strongly correlated particles. All right? So then the question is, well, does the Hubbard model have bad metal or strange metal behaviors? And so I'm going to tell you about is both the theory, what we understand about that right now, and also the current cold atom experiments and what they have already told us about strange metal and bad metal behavior in the Hubbard model, and what they're going to tell us in the future. All right, so I'm going to start with just maybe a recap of last night's lively debate. What is a strange metal? What is a bad metal? So I think it's pretty universally defined that a strange metal is material where the resistivity does not obey what you expect from Fermi liquids. In particular, the resistivity is proportional to the temperature. A bad metal, the classic Mott definition is that if you interpret your resistivity in terms of a Boltzmann equation, in terms of a Drude model, that your mean free path is shorter than the lattice spacing. All right. The literature also contains another definition, which is just that the resistivity is above h over e squared. And that will be relevant later, but I subscribe to the first one, the Mott one. So, all right, so there's been three cold atom experiments, or three major sets of cold atom experiments investigating exactly this question. The first one is from a group at Princeton, by Wasim Bakr. And here you have photographs of cold atoms, and they're not resolved to single site level, but you're seeing just a cloud. The darker the color, the more particles there are. And Wasim's working with a 2D gas, and the way he extracts resistivity is he applies a superlattice potential, which then creates a density wave, and then he looks at the relaxation of this density wave. He repeats that for different wavelengths of lattice and can extract a diffusion constant, and then uses an Einstein-Nernst relation to then get a resistivity. All right, beautiful set of experiments. There's a second group at the University of Illinois led by Brian DeMarco, and what they do is they directly measure the momentum relaxation time. They use some sort of Raman-type optical excitation to take particles from one area of the Brillouin zone and shove them into another, and then look at how that non-equilibrium distribution relaxes. All right, and that's a 3D experiment. The third experiment is Joseph Tywison's group up at Toronto, and what they do is they have these 3D gas in an optical lattice, this Hubbard model, and they add to that a harmonic potential. And they look at just the sloshing mode in this harmonic potential, right? And by the behavior of how this thing sloshes back and forth, you can pull a resistivity. All right. As is clear from this, it's hard to, these experiments don't look like you're hooking up a battery and measuring a current flow, right? That's always one of the challenges with cold atoms. But I want to instead flip that around and say the good thing is this is not that you're hooking up a battery and looking at a current flow, is that you're getting access to things which are actually very hard to get access to in the solid state systems, right? You can directly measure relaxation times. You can separate out what's happening to compressibility and what's happening to diffusion. And I think this is really valuable for breaking down what's happening in these very strange systems. Yeah, please.
So in all of these systems, is it clear that you have a large enough Fermi surface so that umklapp scattering is responsible for having a finite diffusion constant? Because presumably these are otherwise clean.
You're anticipating my talk. So the question was about umklapp scattering and what happens when you have very small Fermi surfaces or very big Fermi surfaces. And indeed, Joseph Tywissen's group here has some very nice data where they see that the resistivity becomes very small when you have a low density. So yeah, beautiful. All right, so that I've given you sort of the experimental landscape, what people have done. I haven't told you their results, but I've told you how they did it. I'm now going to briefly go through the theoretical landscape. Let me just check my time to see how I'm doing. Oh yeah, I'm doing great. All right, so I've broken things up into 3 regions. All right, up here we have the high temperature region. All right, over here we have a weak coupling. Oh, all right, so Hubbard model. There are 3 parameters I'm going to need to describe what's happening in the Hubbard model. There's a Hubbard U, that's the interaction when 2 particles come together. There's the Hubbard T, that's the hopping. That's in the 2D model, which I'm going to talk about, the bandwidth is 8 times that hopping. Is a nice scale. There's the temperature, and then there's filling, right? How many particles you have. And I like to think about the ratio of U over T as one dimensionless parameter, temperature over T is another one, and then the filling as the third. And so in this space, I'm going to talk about 3 regions. The high temperature, where the temperature is large compared to the bandwidth. Weak coupling, where this ratio U over T is a small number. And strong coupling, where this ratio U over T is a largish number. And I've sort of real cartoon put where some of the experiments are. This is take this with a grain of salt. This is just a cartoon. And I'm going to start by telling you about this high temperature regime, then about the weak coupling and the strong coupling. And I think one of the take-home messages is by thinking about this weak coupling limit, one actually gets a lot of insight into what's happening. Okay, so to start with, high temperature. So if you have a single band model, or even some model that has a finite spectrum, the resistivity diverges at infinite temperature. Right? This is a completely unphysical limit. Right? There's no material we have that has really a finite spectrum. But the way I like to think about this is actually come from weak coupling again, and think about the occupation of states in momentum space. All right? At very high temperature, all states are equally likely. So this occupation is uniform. So if I apply an electric field to this thing, what happens is these particles march along in k space, higher k, and nothing happens. It looks exactly the same as it did before, right? So the effective mass is infinite at infinite temperature. You apply as hard as you push, you get no current. Okay? And then if you do the first corrections to that, so the conductivity vanishes, the first corrections to that as you lower the temperature are linear in T, so the resistivity scales at 1 over T. So quite generically, in models with bound spectrum, you get a 1 over T resistivity. And you can do this in this weak coupling picture, or you can do the same sort of arguments in strong coupling. More or less, you take a Kubo formula and you just literally do an expansion in 1 over T, and you argue that the various terms are well behaved, and so it's actually the leading term.
Did you mention say 1 over t.
So I was saying expansion of conductivity is usually what you do. You expand the conductivity in 1 over t, and so that gives you a resistivity that's linear in t. Exactly. Actually, another nice way to think about this story I just said here is that you know that particles at the bottom of the band, they have a positive effective mass. Particles at the top of the band have a negative effective mass. And so at very high temperature, you have as much contribution from this positive effective mass region as from the negative effective mass region, and that ends up giving you 0 effective mass, or infinite, 1 over m's you add. Okay, so one thing that's going to complicate our thinking about this model is we have a linear in T resistivity for this trivial reason, at least if we were at high temperature. I would like to not call this a strange metal, but I'm not sure how exactly you threw into the definition. I would also not call this a bad metal because although this effective mass diverges, the mean free path can still be very long, right? So that works in the Mott definition. Okay, so that was high temperature. I'll now tell you about weak coupling. All right, so these are results of calculations of one of my students, Thomas Kiley, and this is just writing down a Boltzmann equation, doing expansion in U squared. So this is all very well controlled stuff. All right, so the picture that comes out is that all of the scales of resistivity just go as U squared. So I don't have to show you U in this diagram. That just sets a scale of the resistivity. And so everything is really just as a function of filling and temperature. And there are 4 regions that one finds. So first of all, there's this large region where you get T linear resistivity, which has this nice V shape, which seems familiar from other talks that we've seen, which just takes that high temperature region we were talking about and extends it down to lower temperature. There are also these regions I've colored in blue where you have resistivity that scales as T squared. That's all explained. That's the standard Fermi liquid expectation. And then finally, at very low filling or very high filling, because of this Umklapp gap, because you don't have any collisions which can reduce your momentum, you actually have exponentially small resistivity. All right. So let me just repeat that last bit. So what's going on here? So in these systems, this is just Hubbard model. There's no phonons. There are no impurities. So why is there resistivity at all? Why does the momentum relax? And the only momentum relaxation mechanism is particle scattering, particle-particle scattering. So I have 2 momenta K1 and K2 come in, 2 momentum K3 and K4 go out. And if there wasn't a lattice around, the total momentum would be conserved. But we have a lattice, so we can cheat momentum conservation by a reciprocal lattice vector, which means that the lattice is absorbing that momentum. Right? So you're allowed to add this lattice wave vector. And if your Fermi surface is very small, there are simply no reciprocal lattice vectors that take you from the Fermi surface to the Fermi surface. Right? And so you simply have no resistivity. You have no scattering. One minute.
Question?
Sure. Yeah.
Even with Umklapp, you can only relax. You can't relax the total momentum mod Q, right? Mod reciprocal lattice vector.
I mean, an interesting thing to think about. So what Alan was saying is that if I sum the K of all of the particles, then this sort of thing means that sum of the K mod Q is constant. So if I imagine there's a large number of particles, so the momentum per particle, it's like when you're dividing numbers and you have some remainder. So it's going to be some remainder we can never get rid of. I think that's a true statement. It's probably very hard to see, though, again, because there's a large number of particles.
Okay.
Absolutely. Okay, so now, if we go away from this limit where there's this Umklapp gap, all right, go to some generic filling. All right, so here's a picture of a typical Fermi surface. And I take a particle with momentum k1, and I look at how many other particles on the Fermi surface are there to scatter off of. The number of such particles is going to vary linearly with t, because I can only scatter with things that are within t of the Fermi surface. Right? And then you ask, those two guys scatter, and you look at the final momentum they go to. You have to conserve energy, conserve momentum, and be within kBt of the Fermi surface. Well, the number you can go to scales as t as well. And so that gives the standard scattering rate scales as t squared that we're familiar with. All right. If, however, you're in this nearest neighbor square lattice Hubbard model, you're at half filling, you have a nested Fermi surface. And with this nested Fermi surface, if I take two particles and scatter off them, they automatically end up back on the Fermi surface. And so instead of having this scattering rate goes as t squared, it only goes as t. Right? Another way to say this, which might connect to some of the other things people have talked about, is that if I look at the what's this? If I look at the effective the band mass, that at half filling in this model, the band mass diverges, right? Okay. One feature of this is not only at half filling there's something interesting, but just proximity to half filling means that the temperature scale of the crossover between quadratic and linear T resistivity is at a very low temperature. Right? And if you went to, you might also say, oh, this is very special to this nearest neighbor Hubbard model, let's put in a T prime or something. I mean, clearly putting in a T prime is going to make this no longer go exactly to 0, but the smaller that T prime is, the lower that crossover temperature is going to be. Okay. I have to skip this. All right. So that's sort of the weak coupling picture. I'm now going to tell you a little bit about strong coupling. And this is really stuff I've gathered from the literature, primarily these three sets of numerical experiments done. One's a high temperature expansion, one's Monte Carlo, another is a dynamical mean field theory. And so here's sort of the cartoon that I've came up with from these papers. But one thing I want to say is that when you go from weak coupling to strong coupling, there's no phase transition in the normal state. So things should be somewhat continuous. And when we look at the weak coupling model, I said we have this huge range of linear and T resistivity. So there's always going to be the problem in the back of our mind is that if we see weak linear T resistivity in the strong coupling model, is this nothing but that same physics coming out? Or what are we going to do to diagnose that there's something interesting in it? And I don't have a full answer to that. I have a few little peeks to it, but it's good to keep in mind. Okay, so the typical features in the strong coupling model are very similar, and I've used the same sort of colorings to describe them. There's a few new things. So one, when you have strong interactions, you can get Mott physics, right? You can get a Mott insulator at half filling, and in addition to that, when you're proximate to that Mott insulator, you're going to get enhanced resistivity. So I've sort of drawn that as this little red thing, and the numerical data looks like there's something vaguely reentrant about it, that you go through a region where the resistivity grows, and then as you keep cooling, it then starts falling again. That looks metallic. If you're doped away from half filling, that eventually it's metallic, but at high temperature, it looks like it's going to be a insulator. All right. Another really curious feature, this is a little bit of a fine detail, that as I drew it here, I have some region where this linear and T resistivity goes all the way to 0 temperature. Right? And you can look at the data and debate exactly how true it is. But if so, this would definitely be some sort of exotic strange metal thing which is not continuously connected to the weak coupling physics. In the dynamical mean field theory paper, they attribute this to spin fluctuation physics. I have no idea if this is related to stuff in the materials or if it's, you can have multiple. As we've seen, you could have the same phenomena, linear T resistivity, with different sources. Right? I think that's definitely clear. So here, a big challenge is that cold atom experiments aren't cold enough to really tell us the answer to these things. Okay, so I think I'm in my question period, but I'm gonna pretend I'm asking myself a question, and just tell.
That's brilliant.
And tell you what you should be asking. And the first is, okay, so I told about the experiments, I told about the theory. What's been seen in the experiments so far? All right, so the first thing is they've seen linear T resistivity. Yay! All right, as I said, how profound that is not clear. Okay, but they've seen it. They've seen resistivity that exceeds h over e squared. All right, so by some measures, that's a bad metal. That's great. Huh?
In 2D systems.
In 3D as well. I mean, 2D is probably where you care about this, but yeah.
Quick question. That's not the units of resistivity, right? What provides the length?
It is in 2D.
It is in 2D. Yeah. And of course, they're chargeless, so I throw in an E as a it's dimensionless E. They've seen this Umklapp gap that you asked about, and they've had direct measurements of the relaxation rates. And sort of my cartoon of where the experiments are is this, they're right above, right around where there's interesting things. Okay. I think the real experimental promise, though, is not in, measuring things which you can measure in materials. It's in measuring different things. And so Martin gave this great talk where he was showing these pictures where he's looking at where every particle is in a lattice, and by looking at the correlations between these, he's able to say something statistically about pairing. Or there's some experiments looking at similar physics, what Randy was talking about, where you look at actual dynamics of watching spin charge separation happening. I think this is where the real fun is. All right, and with that, I'll let you guys ask some of your own questions and not guess what they're going to be.
Thanks for a beautiful talk, very clear. I think one surprise in Wasim's data seems to be that, so Wasim Baker did this data on in 2D, observing linear and T resistivity, going through this dashed line that you have here, the what you're limit, so not only above but also below. Okay, it's 2 data points, but still they seem to see the same slope as you go through. So I think that is maybe something to focus on, and also experiments need to provide more data points there clearly.
Yes, let me, for those who aren't as familiar with the experiment, so I talked a little bit about this experiment. This is their data of extracted resistivity versus temperature. And these red points are their data points. Temperature is being measured in units of the hopping. As I said, the bandwidth is 8 in these units. And so they've gone down to, I don't know, 0.2 T roughly is their things. And you look at these red points, and wow, those are a really beautiful straight line. That's great. This dash thing here, that's the resistivity equals h over e squared. As I said, I don't care about this line. It has absolutely nothing interesting as far as I can tell, right? So the important thing for me is what's happening to the relaxation time, what's happening to the mean free path, and nowhere they actually directly measure the relaxation time, and they never have a case where the mean free path is shorter than the lattice spacing. So they, in my mind, they haven't passed the MIR limit. In terms of temperatures where they expect some deviation from this high temperature linear in T. So down to this temperature at weak coupling, we also have exactly linear in T. So it's...
What is the band filling there?
I think it's like 0.36 or something, or 0.4 something. You know, it's quite generic.
Is the offset at zero temperature to be taken seriously? It seems to extrapolate to a finite resistance at T equals 0.
I don't know. This is what the data is.
But in perturbation theory, you wouldn't see that.
That's right. So weak coupling, we definitely the resistivity vanishes at zero temperature via polyblocking. Yeah.
I wonder what your perspective would be. Sorry, here with the mic, it's hard to tell what the acoustic is. So it's clear, and I hope you agree, that at high temperatures it's no surprise you get 1 over T conductivity, right? So that's a classical limit in some sense if you have all the SI energy states. So the real question is, where experimentally does this appear, and can perhaps the simulation is called Adams mimic that? And there are people in this audience who know more about this than me, but from what I understand, there are two classes. One is a doped mod insulator. So in your diagram, one should look right where that atomic bomb has exploded in the center, right?
Yeah.
And the other aspect is if you have, not necessarily a half filling, but if you have an order parameter that goes to 0 and perhaps you approximate the quantum criticality. So could you say from your perspective, in cold atoms, is there hope to approach 1 or 2 of those?
Yeah, great question. So absolutely, I like the description of the atomic bomb picture. That I think the experiments are right there. So I think that there's technical issues related to seeing things, but I think seeing an upturn of resistivity due to that Mott physics, that's going to come in the next year or two. I think seeing this very low temperature stuff is going to be very tough. I think while it's exciting to see this upturn resistivity here, we know it's there, right? It's not going to come something new from that. In terms of systems where there's some other kind of criticality going on, I think that's a great thing to look for, great thing to play with. There are, temperature is always a problem. Trying to get the transition temperature sufficiently high. Randy has some nice stuff looking at magnetic transitions and getting close to those. So I think wait a couple years, we'll get there.
So you have two mechanisms for the linear T, right? So one is the very high temperature, and the other is the nesting.
Yep.
Now, presumably the nesting mechanism is less robust, right? So as you said, if I can just turn it on. So when you transition from high temperature, the very high temperature, to the low temperature at half filling, is there like another line that tells you how you go from the high T physics versus the nesting physics?
Yeah, so I think there's a coincidence in this particular system with its dispersion that the linear in T resistivity at high temperature has essentially the same slope as linear T resistivity at low temperature. It's not exact, but it's close enough that by eye, if I look at this green curve here, which is the half-filling data of resistivity versus temperature, it looks like a beautiful straight line. But if you really look carefully, it actually has a little offset below at low temperature, higher temperature. If you played with your band structure a little bit, you can get those two to be more different from each other and actually see a transition.
Yeah, but so if I just turn on this t prime, presumably you're going to have the t squared. Gradually, you get a t squared, right? So, but is there like a transition from the high t? So let's say you turned on this t prime, so you get this t squared. So is there like a transition from?
It's a crossover. It's a crossover. It's a smooth crossover. Yeah.
Last question, while Shaggy, can you comment?
So going from your very high to your even higher temperature regime where you should see infinite resistivity, can that be at least a trend of change in trend we see in the code?
So the data that I showed of this which was around from temperature of like 0.2 hopping to about 10 hopping, that's really in the transition where you're going between where things are partially filling the band to almost completely filling the band. And the upper end of that is really that ultra high temperature limit, I would say.
But shouldn't there be a deviation from the linear temperature resistivity then?
So at infinite temperature, the resistivity is infinite,
Yeah, so
which is
somehow
just
you
that
have to
1 over
go
t.
from linear to
No, but that's exactly.
It will always
Linear and
be-
t, if you take t to infinity, it goes to infinity.